information that's given to us. In this case, the diagram is going to be most of the information we need. They do tell us that weight W is 1,000 pounds. So I'll include that here. But that will also be in the free body diagram that we'll get to in a second. In this problem, we're asked to find what are the tensions in the cables to maintain static equilibrium and the force in the rod to maintain static equilibrium. So I'm going to name those the TAC for the tension in cable AC, TAB for the tension in AB, and then FAO for the force in the rod. So again, the way at least I'm doing my notation here, I'm using T if it's something I know must be in tension, and generally I'll use F if it's something that could be in tension or compression. And this will help me at the end assess, as a quick check, that the tensions have to be positive, but these general forces, the things with F in them, could be positive or negative and still be feasible, since the rod could be compressed or put in tension, and that would be okay for this system. All right, so 3 forces that I'm trying to find, 2 of them I know are tensions, 1 of them could be either. Free body diagram, we still have to pick our point of interest. So in this case, which point are we going to model the forces acting on it? So if we look at A, the weight's hanging from it, cable AC is attached to it, AB and AO. So if we choose point A as our point of interest, all 3 forces we're interested in act on A, and the weight will also act on A. So that is our point of interest here, is that point A. Yeah, so making it bigger, I have my point A, and I can put the coordinates of point A. Since we're in 3D, that's going to be helpful to us. So in the x direction, to get from the origin to A, just writing these coordinates down, I have to go in the x direction by 15 inches. In the y direction, I have to go 48 inches. And it's in the xy plane, so 0 in the z. And this is in inches. And there is well, I'll put all the important points first before I start putting forces on. I have a force that will go from A towards the origin. That's the force in member AO. Now the origin I know is at 0, 0, 0, so I don't need to write that one down. I'll have a force from the cable AC that goes from A to C. So I'll need to represent point C here and put its coordinates. It's in the YZ plane, so it's going to be 0 in the X. I have to go 48 in the Y, and I have to go 36 in the Z. And a force that goes from A to B from that cable. B is in the XZ plane, so I have to go 15 in the X, 0 in the Y, and that is going to be 36 in the Z. Now I can put the forces that act on AO. So again, I have these cables and these, this force in the member here that will act along that same direction. So going from A towards C, I'll have tension AC. Going from A towards B, I'll have that tension AB. And going from A towards O, I'll have FAO. And also acting at A, I have the weight, which I was told was 1,000 pounds. So 4 total forces acting at A. 3 of them I don't know their magnitudes, but I do know their directions. And then I have this weight force of 1,000 pounds. I do know its direction and its magnitude. I have forces with labels. I have a right-handed coordinate system. I have my point of interest A, and I have the proper dimensions. In this case, I'm using coordinates, these 4 coordinates as my dimensions, which I'll need in the next step to find the unit vectors, which I'll need to find my sums of forces x, y, and z. All right, so when I'm in 3D, either with particle equilibrium or later with rigid body equilibrium, I know I'm going to have to be using unit vectors in the equilibrium steps, so I usually like to start with those first. I know I need to know, in this case, these 3 unit vectors to write my equilibrium equations. So I'm going to start with that step and then write my equilibrium equations, and those will be easier to write then. The order I do it in doesn't really matter. I know I need to find the direction that goes from A to C. So for that, I have to take the end point minus the start point and divide it by its magnitude. So I have to find RAC and divide it by the magnitude of RAC. RAC is going to be 0 minus 15i, so minus 15i. 48 minus 48j. And 36 minus 0k. And this will have a magnitude of 39. So unit vector AC will be negative 15 over 39i plus 12 over 13k, if I reduce it. Sorry, this is negative 5 over 13. Did the wrong one here. And then the j is 0, so I won't write that here. Negative 5/13 I plus 12/13 k. For U hat AB, I'm going to use the same process. I'm not going to write all the intermediary steps here. But I have to find RAB over the magnitude of RAB. So that's going to be the 15 minus 15i, 0 minus 48j, 36 minus 0k, and I have to normalize that. So same procedure as above. I'm going to get that UAB will be negative 4 over 5j plus 3/5 k. And finally, AO, same procedure, endpoint minus start point, so 0 minus 15, I, 0 minus 48j, 0 minus 0k. Normalize that the same way I did in the previous 2 steps. And I get that for UAO, this I have in decimal form, 0.299I minus 0.954j. So all this I do before I get to my equilibrium equations. It's going to make those much easier to at least write down, not necessarily easier to do in the solve step. But any questions on finding unit vectors? All right, so why did I do this? I'll kind of do this before I get to the equilibrium equations. Again, I can write vector TAC as its magnitude times its direction. I don't know its magnitude, but as I just found, I know its direction. So this can be written as negative 5/13 times TACI plus 12/13 times TACK. So what I'm going to be doing without writing this out every time is when I want to know how much of a force is in, say, the x direction, for example, with TAC, this is how much of it goes along the x direction. The negative 5/13 times its magnitude. In J, it doesn't have a J component, so that would be 0. And in K, it's 12/13 times its magnitude, so this is how much of the vector acts in the Z direction. So I use that same idea for all 3 of these, and I use that for the 1,000 pounds in order to develop my equilibrium equations. So I won't write this step out, but that is what I'm doing in these steps. Now I write my 3 scalar equations, sum of forces x, y, and z, and I pull out from my unit vectors the appropriate quantities. It's in equilibrium, I know it's equal to 0. So now I want to put the x component of every force that acts along the x direction. So I can start by looking at the unit vectors that I wrote up here before. I want just the I components. So in this case, associated with tension AC, negative 5/13 of it times its magnitude is how much of it acts along the x direction. If I look at the tension in AB, it does not have an I component, so it will not have anything in my first equation. And then for the force in AO, I know it's going to be negative 0.299 times its magnitude of FAO. And my 1,000 pounds acts only in the negative k direction, so it will not appear in this equation. Right, so equation number 1, I have two unknowns, these two unknown magnitudes, and I just have one equation, so I can't at the moment solve it. Now I do the same thing in the y, and this is why doing all these unit vectors up front will make this much easier. Now I just pick out y components. AC does not have a j, so it will not be in this equation. AB is going to be negative 4/5 times its magnitude, AB, or TAB. And AO has a y component, so negative 0.954 times FAO. I now have a third unknown, TAB, between two equations, so I can't solve it at the moment, so I will go on and write my now third equation because I can sum forces in the z direction in 3 dimensions. So TAC has a component 12/13 times TAC. AB will be 3/5 times TAB. AO does not have a k component, so it will not be in equation number 3. Again, I want to look back at my free body diagram each time. This 1,000 pounds is parallel to the z, and it's acting along the negative z direction. So in equation 3, this is where that weight force is going to be included, that negative 1,000. Looking at these 3 numbered equations here, I have a total of 3 unknowns, TAC, TAB, FAO, and I have a total of 3 unique equations. So at this point, I at least know that I have a solvable system, if nothing else. Now, the actual numerics of it might not be easy to do by hand, but at least I can say it's a solvable system. There's a unique answer, or we expect there to be a unique answer for TAC, TAB, and FAO. So again, 85% of the problem is done. We know it's solvable. Solving it is the next step that we have to take. Questions on forming our solvable system of equations here. There's no springs. There's no extra equations we need here. The x, which is TAB, we got 832. This is in pounds. TAC, which was y, we got 542 pounds. And FAO, that was the rod, we got negative 698 pounds.